Okay, we have started recording again. I wanted today to talk more about, I don't know, some of the classical ways of doing classification. And there was this great guy named Fisher, and he was the he was the proponent of great probabilistic um, ideas. There's something called the Fisher information. And what we're going to talk about today is the so-called Fisher discriminant, which is the way that you take data and that you separate it and that you analyze it. It's a classical result, and I think you'll find it just fascinating. Fisher, it's kind of interesting. There's been a conflict when I used to do work with Boeing, and there were different statisticians, and some were Fisherians and some were Bayesians, and these guys didn't like each other. It was really funny. It was like clowns fighting mimes. You know, they were both trying to do the same thing. And I don't know, maybe someday we can get into the difference between Fisherian and Bayesian sort of thinking. But you know what it boils down to? I think it's reducing to practice. And if you can reduce something to practice, you're going to be good. And both Fisher's and Bayes' stuff has been reduced to practice. I think I mentioned, for example, that your spam filters are all Bayesian, for example. Okay, so let me go ahead and try to share my screen here and do a little bit of drawing. Okay, let's see. Okay, whoop, I gotta go over here and close this guy. I have two screens open, but my pencil doesn't work if there's two screens. Okay, here's a problem. Okay, we have this data in high dimensions. And here's my data in high dimensions, if you will. And we are going to have good guys and bad guys. So this is going to be Fisher discrimination between two possible classes. So we have over here, I'll do these with circles too, red circles. No, I'll do them solid for Sam here. I'll fill them in. So we have this data, and imagine this in higher dimensions. We're only going to do it in 2 dimensions, but I think you can see, you'll be able to see the idea. Now, the question is, and Fisher considered the following question: we would like to project this onto a line. And so we might have a signal in 50 dimensions, but we would like to project it onto a line. So one of the ways that we could project it onto a line is on this line. So we could project it down and we would get, for example, we would get this result, and we would get a point here and a point here. You get the idea? Now, it turns out the line that I chose was a pretty bad line. So we would get values on the line, and plus we would get the blue points on the line too, right? Well, it turns out if we chose this line, this is not a very good line to choose, because you can see all of the data is kind of scrambled up, right? And what we'd like to do is we'd like to choose that line in some way where this data in some sense is separated from itself. And I think you can see, hopefully you can see that if we had chosen this line over here, that we would have had better results, that we would have had like a red here. We would have a red here. We would have a red here, and the data would still overlap. And by the way, typically data does overlap. It's very rare that we have true separated data. And so the blues would be here. And then the point is if we could do this, then we could do kind of a threshold determination. I think you can see that what I'm drawing on right now is a much better separation because it separates in the projection the blues from the reds. Whereas over here, if we were to choose this direction, the blues and the reds would be all scrambled together. And so what we would like to do is we would like to, in some way, assure that the data is spread out and maximally separated. That's what we would like to do. Now, how do we do this? And this was the question that Fisher asked. One of the nice things, especially in Fisher's area or domain, is this allowed very nice visualization of the data, right? You could take this 35-dimensional data and you could project it down into a single dimension. And then once you had a dimension, you could apply your ROC technology, remember the receiver operating characteristic, and you could apply a threshold, for example, here. And you would announce everything above that threshold is red, everything below that threshold is blue. And that would be kind of your detector. Now, here what you have is your ROC curve. This is exactly the ROC curve that we looked at last time. So we move it this way. Your detection and your false alarm probability are going to change. If you do it in this way, they're going to change. And you obtain this ROC curve. You remember the beta versus alpha, right? The beta was the detection probability, and the alpha was the false alarm. And we had a curve which kind of looked like this, which was the ROC curve. And we can see that as the detection probability increased, the false alarm probability would also increase, and that's no good. So that's what we do. We project it down onto one line. Hopefully, if we have maximum separation, we can choose a threshold which separates these things. I mean, if we did a threshold over here for this poor projection, that would really be bad, right? I mean, we would just have a terrible ROC curve. I don't know what it would be, but it would be just terrible. So this was the problem that Fisher was considering. Now, how do we do this? How did Fisher figure out what this line was that we could project on? He said, okay, let's have an axis here, and we're just going to do this in 2 dimensions. We're going to have an x1 and we're going to have an x2. And what x1 and x2 is a point in our feature space. And we are going to have a unit vector here, W. And W is going to define a line, right? W defines a line. And if we have a value here, and let's call this x naught, then the projection onto this line we would call y naught. And it turns out that y naught is nothing more, if you remember your geometry of such things, is the unit vector times the other vector, right? And the question is where to choose W. So that's going to be our quest, where to choose W so that all of this data projects into a line with that gives us maximal separation in some fashion. Well, in order to do this, I'm going to erase here. In order to do this, one of the things that we probably need to do is we need to do, because this is what Fisher did, is we have to take our data here's our data for one, and here's our data for the other one. And the first step is to find the center of mass. To find the center of mass of the data. Now over here, the center of mass might be, I don't know, I'm just eyeballing it here, but the center of mass might be here. Now the center of mass is best thought of if all of these points were on a plane, where would that plane balance? What point would it balance at? That's always the way I like to think about it. And whereas up here, you might find the center of mass here. So that would be the center of the mass of the data. And in order to figure out the center of the mass of the data, we're going to do N1 as the number of points, the number of data points over here. We're going to have N sub 2 as the number of data points over here. We good? And so we're going to have two classes. We're going to have two classes. We're going to call this class the second class, and that we're going to denote it by a chi2. And over here, we're going to have this class, and we're going to denote this by chi1. So the training data is either in chi1 or chi2. It's in one of the classes. So with that, what is the so-called mean? Well, the first mean, and we'll call this M1. We'll use the same subscript as we do for the class. M1 is going to be a vector, and M1 is simply going to be the average of all of the x's in chi1 of x, well, all of the x sub, let's see. Yeah, let's just do this. That's good enough. So we're going to sum up all of the x's and I1s. This is how you take an average, right? And that average is the sum of the mass. Trevor, your brow crinkled. You okay? You following it? Okay. So we're just going to take all of these vectors. We're going to add them up, and we're going to divide by M1, and that's going to be the mean for number one. The mean for number two is likewise, it's going to be 1 over N2 times the summation of all of the x's in the second class of the x's. Okay. So that's going to give us the mean, and this is going to be mean 1. Over here, we're going to have this vector, which I say is mean 2, and we just simply do them out. Now, here's the interesting thing. This is going to exist in this space. Okay, and this space is going to have the W here. Okay, now you'll notice something interesting is that the projection on here is not limited by the fact that this W goes through the origin. If we were to have a line down here, the projection on that line would be the same as the projection on the line that went through the origin. Make sense? So it doesn't matter where this is up or whether this is down. So let's have it go through the origin. So that's nice and convenient for us. So here's the interesting thing. What we'd like to do is we'd like to take this point and we would like to project it onto this line. And this is going to be a value which we're going to call M1 and give it a little twiddle here. And this one is going to be, the projection onto the line is going to be M2 twiddle. So we are going to project the means onto the middle of the line. And so these mean projections, if we do M1 twiddle, that's going to be equal to, as we said, that's going to be omega transpose times the mean, right? Times the first mean. And, you know, this is kind of interesting because this is the same as this 1 over N1. And so this is nothing more than this. And I have no idea why I'm writing on a 45-degree line, but that's the way it turned out. Okay, here's what's interesting about that. When we project all of the blue stuff onto this line, here's the line, here's all of the blue stuff. we project onto this line. And then we have the center of mass here. And the center of mass is projected onto this line too. This is M1 twiddle. That wasn't very pretty. You'll notice that this is nothing more than the average of all of these projections. In other words, on the line, if we took this number plus this number plus this number plus this number plus this number, divided by N1, we would get M1. So the mean is preserved in that sense. So the projection of this mean, and here's the mean up here, the projection of that mean is exactly the same as if we projected all of the individual points and then took the mean of all of those projections. And that's what this is saying. That's what this is saying. This is the projection of the, this is the projection of each one of the individual points. So we can get this M1 twiddle by doing one of two things. We can either compute the mean in the higher dimensional space and project it, or we can project all of the individual data points on the line and take the average of those. And I think you can see that M2 twiddle is very similar to this. It's equal to 1 over N2 just by symmetry. And this would be all of the x's in chi2 of the x's. So does that make sense? It's kind of very interesting. I think it's interesting. Okay, so we have these individual projections. By the way, we are going to call this the X space. So this will be like X1. I can do better than that. This will be X1. This will be X2. This is the feature space. In general, we'll have like X45, X whatever. And this is going to be Y. This is going to be the Y axis. So we're going to take and we're going to project the multidimensional signals down to simply the Y axis. Now, just as before, we have the two types. We have the class of psi1, right, which is the purple. Then we have the class of psi2, which is the red here. And in a similar fashion, when we project those, after projection, we're going to have this line, which is called Y. And then we're going to have purple points on it. And we're going to have red points on it. And so we're going to give this the designation of being the set Y2. So Y2 is the projection of the psi2. And in a similar fashion down here, we're going to call these points, the purple points, Y1, just so we can talk of elements in the set. Does that make sense? So chi2 or chi1 projects onto Y1. And in a similar fashion, we have X2 or chi2 projecting onto Y2. So when we talk about chi, we're talking about the multidimensional. When we're talking about the X, we're talking about the lower dimensional. Push on my stop button, right? You hear that?
Yeah, if you press the power button twice.
I don't know if it worked or timed out. This is irritating. I'm going to take Microsoft Teams off of this thing. Otherwise I'll have to master it some way. Okay, so this gives us the means. Now, if you think about this, if we get some sort of mean here, shouldn't have done that. Suppose that we get some sort of mean here, mean 2, and we get a mean 1 here. Or mean 1, yeah. One of the things I think you can see is that we would like these to be separated as much as possible in order to get good discrimination, correct? Would like to have those separated as much as possible to get good discrimination. But that isn't enough because it's kind of like a signal to noise ratio. We're kind of getting the signal here, but we don't have the signal to noise ratio. There's something else which happens. And that other thing that happens is there is a variance. And if you think on this y-axis that we have a y1, I'm sorry, that should not be a y1. We have an m1, a mean for the 1 class, and a mean for the other class. You also know that we have a standard deviation for this data, right? Which you can compute. Everybody knows what standard deviations is. So we have a standard deviation for this class, which we can call sigma 2. And we have a standard deviation for this first class, which we call sigma 1. Standard deviations, as you have to be familiar with, is a measure of, the dispersion of the data or how far the data is spread out, correct? And it seems like those dispersions should have something to do with the best discrimination. So Fisher's answer was is to look at the difference between the two means and then we would like to divide by the standard deviation. So this, if you will, is kind of the signal, and in the bottom is the noise. As engineers, we know that we have a signal to noise ratio. And what we would like to do is we would like to maximize this. Now you notice all of this is a function of W, isn't it? Don't forget that W, which was that unit vector that we were doing. So this becomes an optimization problem. The optimization problem is to find the W that maximizes this difference. Now Fisher had a little bit different idea. But it was very, very close. He said that instead we should consider something called the scatter in each class. The scatter is defined as, well, it's something like the standard deviation, but it doesn't take into account the number of elements. So the scatter in one direction is going to be equal to the summation of all of the y's in y1 of y minus m1 twiddle squared. Now you've seen that, and if we divided this by n1 squared, or if we divided this by n1, it would be equal to the variance. Do you remember that equation? So this is nothing more than n times sigma 1 squared. In a similar fashion, we have S2 squared equal to the summation of y and y2 of y minus m2 twiddle, and that's equal to n2 times sigma 2 squared. So therefore, what he wanted to do was to measure this, not using the standard deviation, but rather he wanted to use the dispersion using S1 twiddle and S2 twiddle. And let's see, I forgot my twiddle down here, so I'm going to put it in there as red. So he therefore defined something called the Fisher distance, at least that's what we call it today, the Fisher distance. The Fisher distance is J as a function of W, because it depends what that unit vector is we choose to project on. J of W is equal to M1 twiddle minus M2 twiddle. That's the signal. And then over the noise, which would be S1 squared plus S2 squared. And I guess these should have twiddles on them. So this is what Fisher did. Now, this is a function of W, right? This Fisher distance. We want to maximize it. How do you maximize something like that? Well, you take the first derivative and you set it equal to 0, right? That's the way that you do that. But what if you have a multidimensional function? This is a function of whatever the dimension of your feature space is. So what you want to do is you want to take the derivatives of J of W with respect to each W sub n, and you want to set those as equal to 0. And if you look at the vector formulation of this, you find out that you are performing an operation which is called a gradient, if you will. It's the derivative equivalent. You would like to set the gradient of JW. Now, what is the gradient of JW? That is a vector in itself, which has all of these elements in them. In other words, this is going to be DJ DW1, DJ DW2, etc. So that's a simple problem, isn't it? Well, you know, Fisher did this, and I was toying with the idea of going through the math, but I think some of you would doze off. So I'm going to give you a reference of how this was derived. But here is what Fisher came up with. He says that the optimal W is equal to SW inverse. Now, this SW is going to be matrix. I like to underline my matrices. That's how you know that I'm talking about a matrix. So it's SW inverse of M1 minus M2. Where SW is equal to the sum of two matrices, S1 and S2. And this S1 and S2 are defined as scatter matrices. And the scatter matrices are defined as S1 the summation of X in chi1. So we're doing all of this algebra in the feature space, not in the projection space. Now you notice here that there's two ways to multiply matrices or vectors together. You can multiply two vectors together and get a scalar, or you can multiply two vectors together and get a matrix, right? This is the case where we're multiplying two vectors together and we're getting a matrix. So we're multiplying for each one of the elements, and this should be an M1, by the way. We're multiplying each one of the elements by x minus xm, and we're taking the so-called outer product. The inner product is where you get a single number. The outer product is where you get a matrix. So we're taking an outer product of all of these products, and that's going to be the scatter matrix. In a similar fashion, we're going to have a scatter matrix for 2, and it's just copying the same thing down again using a subscript of 2. Okay, so those are the scatter matrices. Now you'll notice that this is kind of like W is equal to M1 minus M2. I'm looking here. Yeah, this should be. Okay, gentlemen, I made a mistake up here. This should be the magnitude squared. This should be the magnitude squared. Sorry about that. So this was a goof, which I will advertise. I'm always big at advertising my goofs. So you'll notice that this is kind of like M1 times M2. This is kind of like the signal over S sub W, or S sub 1 plus S sub 2, right? Now, of course, you can't divide by a matrix, can you? But notice it has a similar sort of flavor as this sort of relationship, here. Okay, it has a similar relationship than we have here. So again, I'm not going to derive this, but this is the result that we get. And what this does is it gives you the maximum. This gives you the maximum separation, the maximum Fisher distance, and tells you, and I think this is pretty clever. You know, this guy did this without any computers or anything back when he was developing all of the mathematics. So if you have a bunch of data in higher dimensions, you want to visualize it by projecting it down into a single dimension and then performing your discrimination in that single dimension. This is a very good way of doing it, right? The challenge is, of course, this is a totally linear classifier. It assumes that things are linear. And so it suffers all of the problems that linear classifiers do. Artificial neural networks, for example, are nonlinear classifiers because they use such things as sigmoids and such in order to map from the input to the output. This assumes that there is a relationship among the results. And in fact, what this does is as follows. We have all of this data here, right? And I'm going to illustrate now that it's indeed a linear classifier. We have the different file values over here. Okay, once we get the optimal W, so we get a W, it looks like the W here should be about like this, right? That should be the unit vector. And we have this. And we have chosen the vector. Now, in accordance to the vector, to the projection, we have all of the blue data on one side. We have all of the green or the, well, I didn't do a very good job of choosing my colors there, did I? So let me try again. Yeah, there we go. Okay, we have all of our values here, and then we have all of our blue values over here. So this is in the Y domain. This is in the X domain. This is in your feature space. We've done it 2 dimensions, but you can do it in higher dimensions. Now, what do we do for the classifier? We're going to choose a threshold in accordance to our ROC curve, correct? We're going to choose a threshold. Notice that choosing a threshold here is exactly the same as putting a line here and saying everything on this side is blue, everything on this side is pink. So anytime that you have this sort of relationship where you do a simple threshold sort of equation, you are indeed having a linear classifier. Linear classifiers are noted by having lines which separate the 2 classes. So despite its cleverness, the Fisher discriminant is, I don't know, it has its limitations. Any questions at all? Okay, so let me summarize. This is kind of the summary since we've gone through a lot of math together here. Let's see if I can keep things level. I doubt if I can, but we'll do this as best we can. Here's the summary. Summary is number 1, we want to maximize the Fisher distance, J of W, where J of W is equal to the projected means. This is M1 twiddle, so that's a projected mean. The projected mean, this thing squared, divided by the scattered. And I put these 2 up. So all of these are projected. This is all happening on the Y domain. The solution after we recognize that J is a function of W, it's this vector that we choose. The solution is W is equal to SW inverse M1 minus M2. So this is all done in the feature space where SW is equal to S1 plus S2, the summation of the 2 in-class scatter matrices. And I'm going to underline those because I like to underline my matrices. Where S1, and I'm just going to use S1 or 2, is equal to the summation of X within the class, the chi class, either 1 or 2, of X minus the mean in that class, 1 or 2, times X minus the mean in that class, 1 or 2. And this one's transpose. And so these are all vectors. And of course, the M1, 2s are the mean or the center of mass of the data clusters. So this is the summary of the Fisher discriminant function. Now here's something which is cool. Before I go on, kind of any questions on this? This maximizes the separation of the data.
Dr. Marks, I have a quick thought experiment here.
Sure.
Would you mind drawing just 4 dots in a line somewhere?
I can draw 4 dots on a line. Is this a test? Is this a test, Sam?
No, not a test.
Okay.
Okay. And would you mind switching colors, and then on either side of those 4 dots drawing 4 more? No, those 4 dots are fine.
Okay, let me make them different
Okay,
colors
okay.
as I've been
Okay, great.
doing. Okay, so
and then all 4 of the new dots would be on either side of the 4 dots that we have. Doesn't matter.
I guess I wanted blue though, didn't I?
Okay, so if this, let's say that this is our feature space right here, where everything's on a line.
This is Y, right? This is after we've projected?
No, this is going to be before projection. This is going to be in our X space.
Well, if you're only in one dimension, then there is no projection. I don't know
Right.
what's going on.
So just hear me out. So imagine that this is our feature space, and all of our data just happens to lie on a line.
Okay.
If we were to perform the Fisher distance optimization, would we not get a W vector straight up and down?
Okay, the Fisher vector, we're dealing with a one-dimensional classification.
Right.
In
Well,
that case,
Mhm.
the W vector is only one-dimensional.
Right. So imagine that the data is in a hyperdimensional space, and it doesn't have to be just in one dimension, but overall the data just does lie on a line.
Okay, so you're talking about something like this, right? So here is your space and here is your data. Bear with me.
Mm-hmm.
And I think what you're saying, Sam, is that here's our space. Here's our X1 and our X2, right?
Right. Well, I'm saying that the dots don't necessarily have to lie on an axis. They could be cattywampus as long as they're in a line.
I don't know how to do points on a line with them being cattywampus.
Okay. Well, okay. Never mind.
You want to try one more time? We can try one more time if you want to.
Sure. Would it be okay if I drew it real quick?
Sure. Let me give you control and let's see what question you have here.
Sorry, it's just a weird thing I'm thinking about here. Okay, so let's say that we have this, let's say a 3-dimensional space here, and our point.
That looks like a 2-dimensional space.
Oh, sorry.
Okay, 3-dimensional. I got you. Okay.
Okay, sorry. So let's imagine that we have, hold on. Okay, I'll just do. Okay, it's making these in circles, which I don't really like. Okay, let's just say that these 4 data points, so it's not necessarily on an axis, but they are in a line.
Yes.
And then you have 4 more here, and they're on the same line. It seems to me that the Fisher optimization here would choose a W vector like this, because the stand to S1 plus S2 would be 0, even though the means would lie on top of each other.
Yeah, okay. I think I see what you mean, and I don't know if I have an answer. The question is that M1 and M2 are going to be the same, even though the standard deviations are going to be different. So
Right.
It looks like the Fisher distance is going to be 0, which is bad.
Right.
Which is bad. I mean, if you have a Fisher distance of 0, that means you can't discriminate between the two, at least using the Fisher model.
Right. And so let's imagine a new scenario where these 4 dots are shifted over this way just a little bit.
Yeah.
Well, actually, that wouldn't be better. Okay, scratch that. But it's just interesting to me that it seems like the optimal Fisher vector should be like this, that optimization would yield this? Or I guess that's just zero over
M1
zero.
minus M, no, oh, this is it. Well, of course, you want to maximize the Fisher distance.
Right. Well, the S1 over S2 or the S1 plus S2 is in the denominator. And I guess that would just be a 0 over 0.
Yeah,
So, okay.
yeah. So I think that it does work out. So that, yeah, as you do the projection, you're still going to get, you aren't going to get what you wrote down. You're not going to get the projection where all of the points overlap. You're going to get the projection which was the most intuitive, which was just a duplication of that in the higher dimensional space.
Okay, great. Thanks for humoring me.
Okay, that's great. Any other questions? Okay, let me ask you a question here. We have to determine, we have the option. We have the option of using 3 features, maybe sumo wrestlers, height, weight, and what's the other one that we put in? I don't know, a body mass index or something like that. Okay.
It's funny because you said weight, kind of like weight and width.
Weight and width. Oh, that would be interesting. Okay. Height, width, and weight. Okay. Or maybe the aspect ratio might be better, right? Which, but anyway, we have 3 different features. And so these 3 features exist in a higher dimensional space, some for sumo wrestlers, some for basketball players. Okay. Now, when we have this data, if we're given the data, we're going to have some sort of optimal Fisher distance, right? We're going to have an optimal W. What happens if you restrict yourself and you take away the third one and you only look at height and weight? What do you think is going to happen to the Fisher distance? Now, in both cases, it does project down to a single line. So we're not comparing apples and oranges. We're still projecting down into a single one-dimensional line. So what do you think happens there if you get rid of a feature? Does the Fisher distance increase or decrease?
I think it might depend on how different the 2 classes are in that dimension. Maybe like if the 2 classes are, let's say, identical in height and weight, but they have very different widths, let's say. And then if we were to take out that dimension, then our Fisher distance would drop a lot, I think.
Well, the answer is if you remove a feature and go to a lower dimensional space, you are looking at say you have 15 dimensions, you're looking at the projection of those 15 dimensions onto, say, 3 dimensions. And you're going to lose separation. And your Fisher distance is going to decrease. So if you add dimensions, your Fisher dimension is going to increase, but the question is by how much? Right? And let me go down a side road here. The linear classifier has not lost all of its power. One of the things we did not go over here was something called vector support machines. Vector support machines literally take data, explode it into a high dimensional feature space, an artificial space, using something called a kernel. And then once you're in this high dimensional space, they use a linear classifier in order to affect the final result. And vector support machines, in terms of performance, are in the area of conventional neural networks, not the deep convolutional neural networks, but the conventional neural networks. In fact, I wonder, I don't know if vector support machines have been applied to convolutional neural network sort of problems. I suspect they could be if you scratched your head enough. Okay, back after saying that linear classifiers are still in vogue, if even for nonlinear classification. In fact, let me elaborate on that a little bit, and then I'll get back to this idea. Let's see if I can think of an example off the top of my head or the bottom of my feet or some other part of my body. Well, that wasn't very good. Minsky and Papert, when they first came out, they said, linear classifiers really suck. And early neural networks were all linear classifiers. And they said, for example, look at the exclusive OR. Now the solid dots here correspond to a logic 1, right? This is an exclusive OR. You know what an exclusive OR is, right? I'm either going to be on time or I'm going to be late. Well, that isn't a good example. I'm either going to be at the store or home. Okay, that would be an exclusive OR. Now, if I'm at the store, that's true. If I'm at home, it's true. I can't be both at the home and the store. So that would be a 0. That's what this would be. So one option excludes the other one. You know where you use the exclusive OR every day? In two-way light switches. That's an exclusive OR. That's a topic for another time, though. Now, what Minsky and Papert came along and they said, you know what? There's no way with a simple classifier that you can separate the hollow points from the dark points in this exclusive OR. There's no way you can do it, right? The answer is yes. There's no way that you can separate it. No matter where you draw the line, you're not going to be able to totally separate the dark spots with the hollow spots. So they said linear classifiers are really kind of crazy. But imagine going to a higher dimension. This is not exactly how vector support machines work, but it gives you the flavor for what happens. We're going to add a third artificial dimension, which we're going to call x sub 3. And let's say that x sub 3 is equal to x sub 2 minus x sub 1. Is that okay? Now, here are the points before. Before, we have a point here, which is 0. We have a point out here, which is 0. We have a point here, which is 1. And we have a point here, which is 1, correct? Okay, my example doesn't work. That's the conventional way.
Dr. Mark, are you saying that you wouldn't be able to linearly classify that? Because it seems like
you would be able to linear classify that. Yeah, the point is that by adding a third dimension, and I haven't explained it very well, I'm afraid, but by adding a third dimension, you could literally do a threshold right here. And what you could do is you could separate the red from the blue, couldn't you? You could separate the two. So by adding nonlinearities, you get these different results. And this has been known for a long time. And I recently learned that this has reemerged, and it turns out artificial intelligence emerges all the time. And there's this new field, quote unquote new, called reservoir computing, where neural network inputs are subjected to all of these kind of nonlinearities, and they generate this fitness, and the nonlinearities then generate this higher dimensional space where you might be able to do some interesting things. And it generates a so-called reservoir of possibilities that you can go into and mine in order to get the separation, whereas before you weren't able to get the separation. So this, as I see it and I understand it so far, this reservoir computing is nothing more than this old way of doing things. So anyway, that's what happens with higher dimensions. Okay, let's go back now to this idea about the feature, the Fisher discriminant. If you take away dimensions, you decrease the Fisher distance. You agree with that? but maybe by not a lot, okay? And here's the question. If you're doing optimization and you want the best results, maybe you can't use all of the features. You might have, for example, a baseball team. You don't want that baseball team to have all great pitchers, right? You want to make sure that everything is covered correctly. And maybe you have some people that can play different positions with different efficiencies. And the question is if you have 50 sort of different, 50 different players, how do you choose your best team? Make sense? And let's assume that we can indeed choose the team. And let's say we do it akin to kind of the Fisher discriminant. I've messed up the explanation a little bit, but there's a technique called branch and bound for optimality. It's also called backtracking. Has anybody heard of branch and bound at all? It's really a cool way of doing things because it does good stuff. Let me show you what the branch and bound is. We're going to start out with 4 different features. 1, 2, 3, and 4. And this 1, 2, 3, and 4, I don't know, it has some sort of Fisher distance associated with it. We won't worry about that. But the first thing we go over to here is we go over and we drop number 2. So that we have 1, 3, and 4. And we're going to see how we can do without having 2. And all of a sudden with this 1, 3, 4, we find out that in the step 1, and I'm going to call this step 1, we have a Fisher distance of 3. And so this is the step, if you will. Okay, that's kind of cool. And now we're going to get rid of 1. So we're only going to have 3 and 4. Features 3 and 4. This is step number 2. And we're going to have a Fisher distance of 2. In other words, every time I remove a feature, I'm going to decrease the Fisher distance. Make sense? So, okay, is this the best we can do? Is the Fisher distance of 2 the best we can do? Again, our desire is to get this down to 2 features, the best 2 features for doing the classification work. So now we come up here and let's get rid of 3, first of all. And we have 3, and so now we just have the numbers 1, 2, and 4. And it turns out that here, in this example I'm making up as I go, that we have in step number 3 a Fisher distance of 4. Okay, that's well and good. Now we have to take away, for example, another one. So let's take away 2. And we take away 2 and we just get 1, 4 here. And suppose with this in step number 4, we get a Fisher distance of 2. So it looks like 1 and 4 operates exactly the same as 3 and 4 in terms of the Fisher distance, right? But we can also come down here and get rid of, you can see I'm just building a tree here. We can get rid of 1 and just have 2 and 4. And this 1 and 2 and 4 is going to be, and this is going to be our 5th step. And it's going to have a Fisher distance of 3. So far, this is the best, right? This is the best team that we have is 2 and 4. Well, let's come up here now and let's take away 4. With 4, I'm going to have with the next step, this is step number 6, and I'm going to have 1, 2, and 3. This is step number 6. And I'm going to have a Fisher distance of 2. Can anybody tell me why this is so consequential? I can stop my search. Anything I do from now on is going to reduce the Fisher distance, right? Because I'm taking away dimensions. And if my Fisher distance here is 2, I don't have to search anymore because I know that taking away additional features is going to reduce that Fisher distance even more. So I don't even have to worry about this. So if we go to the I'm going to kill that cell phone. My technology is taking me over. Sounds like I feel like I'm living in a Stephen King novel. So we can take away, if you will, let me get rid of these squiggle lines. We can take away here 1, 2, or 3, and look at the next possibilities of 2 and 3, or 1 and 3, or 1 and 2. So this would be the equivalent of this level. We don't have to do that. We don't have to do that. Why? Because we know that it's going to be a lot, it's going to be lower than 3. 2 is a worse Fisher distance than 3. 2 is a worse Fisher distance than 3. And if I take away any more features, this 2 is only going to get smaller. So therefore, I don't have to look at this, I don't have to look at this, and I don't have to look at this. So this idea of branch and bound and there are more sophisticated algorithms for this, but this is the fundamental one. The branch and bound sort of approach to stuff allows you to terminate your search in certain instances, and that's what we're doing here. We're terminating our search.
Dr. Marks, I have a question.
Sure.
Is it the case all the time that your dimensions are independent, so that if you, let's just say that you have these 4 dimensions and you test the Fisher distance removing 1 and then the Fisher distance removing 2. So each of these is comparing with 3 dimensions remaining, where you just have 1, 2, and 3, or 2, 3, and 4, or 1, 2, and 4, or whatever the other one is. Can you just choose the one with the highest Fisher distance and then cut off all the other branches? So can you essentially go down the tree 1 branch at a time, or do you have to follow them to the end?
Well, let's say that we wanted to find the best single feature here. The tree isn't deep enough for that. We would have to go another level before we did any cutting off of search. So
Okay.
here we want to find the best 2 features, right?
Right.
And if we wanted to find the best 3 features, or I'm sorry, the best feature, we would have to go 1 more branch. We would have to go 1 more step down here. So I don't know if that answers your question, but yeah, you do have to get at least 1 final solution before you compare other solutions to it. Any additional questions at all? Okay, what do you think of that? That's pretty cool, isn't it? If you can find a problem that works that way, it gets rid of the combinatorial explosion of doing an exhaustive search. But notice you need some domain expertise, in this case, that the reduction of the dimension reduces the Fisher distance. You have to know that. And so each one is a bound, and if you go further down the tree, it's going to get smaller and smaller. And if you already have something which is high, you don't have to search anymore. Any questions on that? It's really interesting, isn't it? I think it's kind of interesting. Okay, so that's it. And what we've covered today has been the Fisher distance. A Fisher distance is a linear classifier, but again, linear classifiers do survive in places like vector support machines as the back end of the classifier. We're not going to go into vector support machines, but and I suspect that they're useful too in this new field called reservoir computing. Not sure, haven't looked into it specifically, but I suspect that's the same thing. Just like that XOR could be differentiated, could be sliced if we went to a third dimension. We could use a dividing hyperplane where in 2 dimensions we were unable to do it. So those are really interesting stuff. Okay, any other additional questions? Is Min Kun sleeping? No, he isn't. Okay. I just see the top of your head, Min Kun. There, that's better. Okay, everybody, thank you very much. If there's no more questions, let's call it a day. We'll meet again on Thursday, and Sam will present his deep convolutional work. And if anybody else is ready, then I would really appreciate it, because we're going to have a tight schedule getting in the paper presentations and the neural network examples. Okay. Okay. Thank you very much. Be of good cheer.
Dr. Marks, are you still
Yeah.
available to hang around?
Yes.
for a
Yes.
minute?
Yeah.
Okay.
Well, yeah.